Jeremy Rose, partner Comsys UK. Ladies and gentlemen, please put your hands together to welcome him. Also inviting eminent speakers for the session, I would like to invite Mr. Hirokazu MORI. He's CEO, WARPSPACE USA Inc. May I invite Mr. Pranav Kumar Pandey, Head Optical Communication System Division, SAC. We have on the days with us Mr. Nitish Kumar Singh, co-founder and CEO, Astrogate Labs. We welcome Mr. Pranav Kumar Pandey. Ladies and gentlemen, the topic for this session is optical links for satellite communications. The potential benefits of optical Satcom make it a promising technology for revolutionizing satellite communication system, particularly in applications such as space-based internet connectivity, Earth observation, and remote sensing. As technology continues to advance, optical Satcom will likely become increasingly prevalent in the satellite communication industry. And we have today with us this eminent panel to discuss on this topic. The time duration, ladies and gentlemen, for the session is approximately 1 hour, which has opening and closing remarks by the distinguished chair and moderator. And we will have presentations by all our eminent speakers, question and answers in the end if the time permits. With those words of introduction, I would like to hand over to our chair and moderator, Mr. Jeremy Rose, partner Comsys UK. Over to you, sir, for your opening remarks and to kindly carry forward the proceedings. Yes, I'll just try to get
him. Good morning, ladies and gentlemen. How are we off on the AV? Hello, yes. Good morning, ladies and gentlemen, and welcome to this session on optical. Yes, hello, Hiro-san.
Sorry about that.
Nice to meet you. Jeremy, hello.
Yeah, sorry.
So my name is Jeremy Rose. I'm a partner at Comsys in London. We are a satellite communications consulting firm. We've been around for about 40 years. And first of all, I'd like to thank the SIA for putting this extraordinarily interesting conference together, and especially at such short notice. Let me just tell you a little bit about my background in the optical side of things. So I started 40 years ago, a bit more than that actually. My first job was when I was in college. I was interested in satellites and space since I was probably about 6 years old. And the local engineering firm was the Marconi Space and Defense. And so I went there one summer and said, hi, can I get a summer job? And they said, yes, I'm interested in satellites and space and your Marconi Space and Defense. And that all worked out well. I got there and they put me in underwater weapons. And they said, you know, start from the beginning and work your way up. So I spent 4 years doing underwater weapons and anti-submarine warfare. But what was interesting is that we were also looking at satellite laser communications, and this was in the early 1980s, 79, 80, 81. In theory, it was a great idea. In practice, of course, it hasn't really happened until now. Let me introduce the panelists here in no particular order. We have Pranav Pandey. We have Hiro-san from Astrogate and WARPSPACE, yes, and we have Nitish from Astrogate. I'm going to allow them to introduce themselves as we start. Then we're going to go into some Q&A, and then we're going to get some audience Q&A as well. So I think that because we've got a reasonably small number of attendees here, actually a good number. If you want to interrupt during the Q&A, that's probably fine. We can always sort of slap you down if we find that we're moving off topic. So let me just start over here with Nitish. Talk a little bit about your company and the optical communications industry in general. What you're doing particularly. Oh, only one microphone. Okay.
Hey, yeah. Good morning, everyone. We are. As Jeremy already mentioned, so we are a Bangalore-based company, an Indian company working on laser communication systems. When we started, primarily you see why laser communications are becoming important right now is as majority of the satellite applications, specifically Earth observation sectors, are generating a lot of data. Just RF spectrum is not enough. There is not enough RF spectrum around, and you cannot boost the speeds much further. So that's an area that we are working on. Primarily, what we intend to offer is space to ground laser communication solutions, on which we have already developed a satellite terminal. We are developing the ground station. This would be used for primarily low Earth orbit links, typically 500, 600 kilometer altitude or 1000 kilometers land range, and can provide up to 1 Gbps of links. After that, our plans is inherently to roll it as a ground station, laser ground station as a service model to it, while we continue to work on the inter-satellite terminal developments as well. That's another upcoming area, and we are sure, I think in this panel we will be discussing about some of those applications as well.
Well, I'm just going to actually rightly ask you a question. Sorry, do we have any more than one microphone here? Because it's a little bit... right, okay, fine, okay. So let me give that to you.
Right, yeah.
So I'm just going to ask you, Nitish, one just... Right. I hate it when people do that. So Nitish, let me just clarify quickly. I mean, you make hardware or systems or both?
We are making satellite terminals, so we are making the hardware, needed to realize optical links altogether. And the hardware that we are building as of now is a space to ground solution. So that's the satellite part to it, small satellite terminal that can typically be used in CubeSats starting from 6U beyond and all those links. And then there's a compact optical ground station hardware. This one we are building for the ground station. Then the idea is basically to provide it as a ground station service solution instead of just selling the terminals out there. That's we are building towards.
Thank you very much. Okay, so Hirokazu MORI, you're with WARPSPACE. Hiro-san, tell us a little bit about WARPSPACE.
Sure, yeah. So I'm Hiro, please call me Hiro. I'm Chief Strategy Officer at WARPSPACE Group, and also I'm CEO at WARPSPACE USA based in DC. So what we do is more like a system. We provide our optical relay service to Earth observation operators and space station hawks and also government. We are planning to launch several optical laser equipped satellite into medium Earth orbit in 2-3 years. And then basically what we do is most of our prospect clients and clients are in Rio, basically taking imagery there. When they want to downlink more data with less latency, what they do is basically they send the data through laser link to our MEO layers, and from MEO layer to ground, we also use like a RF and a laser com so that they can get the data near real time 24/7. And the data rate is expected to be at minimum 1 gigabps. And we are planning to increase to say 10 gig or 100 gig in the near future.
So what is driving your demand? Is that multispectral EO, Earth observation? It's not comms, it's communications for the multispectral EO market, which is why you need so much data.
Right, yeah. So there are like the two, positive and negative aspect of this, like why it drives. So the positive way is yes, and there are like a variety of like observation is expanding, like multispectral. There are more different kind of sensors, like hyperspectral, shortwave infrared. There are many more Earth observation business coming up, and some of them they have to really send a big amount of data, especially hyperspectral. They cannot really send enough data through existing like downlink capability. Then optical comes in, and if I may add, some more issues in Earth observation is that radio frequency coordination takes a lot of time these days because it's kind of used up by several major Satcom companies, and also, in terms of a swap of the terminal, optical communication terminal is much smaller for the same amount of data rate.
Right. Okay, we'll come back to that, and certainly as far as the regulatory concerns. Okay. Pranav, handing it over to you.
Yeah. Thank you. Good morning, everybody. Myself, Pranav Pandey. I am from Space Application Centers, one of the leading payload development centers of Indian Space Research Organization. So our free space optical communication development is mainly governed by the technological needs of our ISRO. See, for LEO satellites, they are doing imaging in optical domain, and as the resolution of the images are increased in multispectral domain, hyperspectral domain, there is a huge amount of data is being created at LEO satellites, and that need to be transported to the relevant ground station in near real time as per the class of application it is targeted to. So to cater to these requirements, we need optical links to transfer those data either direct to the ground or to through a data link relay from LEO to GEO. So we have, there in ISRO, we are responsible for development of system engineering as well as all the subsystems required for this terminal development. In one of the recent payloads, a few years back, we have tested some of the critical technologies that are required for satellite to ground based optical communications link. We have flown one test satellite over there in geo orbit, and from there we are testing our optical communication links. That is still in the testing phase. Apart from this imaging data generation, we have also requirement for this terrestrial link. The terrestrial communication is being supported by the LEO-based optical intersatellite terminals. So for that, we are in discussion with different Government of India agencies. So to providing a backhaul of services through this intersatellite links, we are developing terminals for LEO satellites also. So LEO satellites, basically there is a constellation of satellites in which all the satellites will be connected with LEO terminals working at the around 1 Gbps data rates. So in that regards, we are developing terminals for LEO satellite also. One more promising need for this optical communications link is for optical feeder links, as we are developing satellites with high throughput capabilities. So to cater to this Indian mainland, we have different optical feeder stations that we call gateway stations. So as the throughput of the satellites is increasing in Gbps, from Gbps to terabits range, and internationally you can see from Viasat 1, 2, 3, the overall throughput is of the order of terabits. So to cater to these requirements, the number of gateway stations will also increase pan-India, which is presently catered using 4 gateway links in India. So to cater to these requirements, optical technologies come to the solution where we can use wavelength division multiplexing based technologies to cater multiple feeder links can be catered from a single ground stations. So we are developing technologies for optical feeder links also in this regards.
So many questions. Let's just clarify for my edification. We're talking here about typically what's the path length in free space of these links?
Path length varies as what links you are targeting. If you are targeting from a LEO to ground link, it is of the order of hundreds of kilometers, starting from 500 to 1,000 kilometers. You are asking for a Leo constellations, so it depends what type of constellations you have worked out with. If it is an interplane constellations at intraplane constellation link only, so it is of the order of 1,000 to 2,500 kilometers at around 700 to 800 kilometer altitude. If it is for interplane also, then it comes to around 7,000 to 8,000 kilometers. Similarly, for geo-based links, it is of the order of 36,000 kilometers. From geo, if it is a geo-based constellation is there, some networks we are also devising for MEO-based constellations, in which it comes around 55,000 kilometers.
So we're used in the sort of the classical Satcom business to talk about beam width as being 2 degrees, 3 degrees. We're talking here about arc seconds, aren't we? I mean, how it's rocket science, isn't it? I mean, if you've got a link of say 2,000 kilometers, what's the beam width of your laser when you get to the other end? Is it we're talking here about a meter, 10 meters, 100 meters?
Yeah, in this way, we can say this optical technologies are a two-way sword. One way it is providing you the highest of the bandwidths available within this spectrum, and at the same time, the beam widths are very narrow, of the order of microradian. So if you are talking about 500 kilometers or 1,000 kilometer link, the beam widths come to the ground at is around 100 meters. So we have to cater that much narrow regions for our pointing and acquisition capability within that range.
Right. So I mean, Nitish, I'm going to sort of ask you because I'm going to try and spread around the questions. What are the really difficult things in engineering in terms of optical links? Is it vibration? Is it well? I mean, I asked the question. Perhaps I'll leave you to answer.
There are some very critical challenges when it comes to lasercom or enabling lasercom, specifically when you talk about mobile platforms. I will start from just the terrestrial comm links. So just previously we were using coaxial cables and all for internet, then came optical fiber. In terms of some key pieces, it's similar to what the optical comm needs, apart from the fiber. So the fiber is basically used as a wave-guided terrestrial comm, but in satellite one space and all, if you talk about through the atmosphere, then atmosphere is the waveguide and all those things. So it's just free space optical comm that we talk about. And it inherently brings a few more challenges associated with it. One of is you have to do atmospheric mitigation if you're talking about space to ground links. For space to space, since there is no atmosphere, it's relatively easy, but the complexity also comes in because these terminals are moving. And imagine the beam widths that we are talking about is 10 microrads to 100 microrads of a degree. You have to have a very precise pointing accuracy maintained, considering the satellites are also orbiting low Earth orbit, typically around 7 kilometers per second are the orbital velocities there. So it's very hard to maintain, and typical satellite platforms are not capable to do it. Most of your satellite platforms, we talk about low Earth orbit, they will typically do around 1 degrees of pointing accuracies. That's just not sufficient. So the terminals itself needs to have its inherent pointing acquisition and tracking systems. See it like a cascaded stage control. So the initial can be provided by the satellites to bring it to 1 degrees, but then later you have to scan the beam where it is coming from and then do it. Then obviously there are scaling challenges. So as I say, in terrestrial communication, there's already optical fiber communication. They also use lasers. But when you talk about space, the link range we are talking about is like 100 times more. So that adds to challenges. How much is the laser power that you can put up? And there are some significant developments on that feat as well happening in receivers. You need to be more sensitive. Then apart from that, you want it for space, so it has to be space qualified. So those are some of the inherent challenges. If I have to pick one, the major is your pointing acquisition and tracking systems. It's a very, very big factor in that, how much beam you can scale. Typically, laser comms, there is no limit in terms of the bandwidth that you can put in. It's just limited to the current technology. In fact, recently a 100 Gbps test has also been done by the one of the NASA academic sciences there. But if you want to scale that, you have to typically scale your beam width as well. So take into account if you're talking about space to ground link, 1,000 kilometers and all, your beam width might be around 100 microhertz or so. You want to go to geostationary, then you will come down to 50 microhertz. There has been links from demonstrated from lunar orbit as well. This was again from NASA, and they were able to achieve 622 megabits per link. And those, the beam width was around 10 microhertz. So at that level, then you need to have to think about the inherent platform vibrations as well, because the vibration itself can add those amount of jitter. So as you scale the beam, again, it becomes a hard challenge.
Yeah, so where's the vibration coming from? Is it just stuff within the terminal? I mean, what are the moving parts?
Yeah, so the moving parts is, see, any satellite first will have its own ADCS system also, typically to maintain 3-axis attitude. Primarily they use reaction wheels, or and these reaction wheels will spin up fast and come down. So they will have some residual jitter. So when I say pointing accuracy is 1 degree, that's one number. But apart from that, there is also performance metric that goes as jitter. So 1 degree, how much accurately it can hold. So those sort of vibrations can inherently do it. If your satellite has mostly reaction thrusters, then obviously it's much larger. That's a change. If you again scale the beam much more, and you're talking about optical communications systems, where you will try to steer it with fine steering mirrors and all, the mirrors vibrations can also add to it. So yeah, those are some of the additional challenges that we need to come.
So Hiro-san, I mean, is it fair to say that in free space, vibration pointing is the biggest challenge technologically?
Right, yes. That's one of the reasons, like most of the optical communication terminal is equipped with some kind of mechanical mechanism to basically track, either it's a gimbal or liquid crystal. Yeah, but yeah, to answer your question, yes. Yeah. But just several other potential issues when it comes to system level, because the higher data rate means internal system within the spacecraft. If it becomes 10 gig, 100 gig, we have to think about how to transfer the data inside spacecraft as well, because existing spacecrafts, they're not really ready for 100 gig or 1 terabit of data flow. Yeah.
So summarizing, the demand is caused by well, just one question. What's the difference between multispectral and hyperspectral? Hyperspectral is just like lots more than multispectral?
Yeah, there's no certain definition, but hyperspectral typically has more than 50 different frequency band. Yeah, multispectral, I think up to like 10, 20 bands. Yeah, right.
So you've got a shed load of data, and it's just a lot easier to do it with an optical link because just the bandwidth is just a lot greater. So that's the simple demand, and the major challenge is the vibration. It's the pointing accuracy. What happens if somebody decides to regulate optical communications? Is that something which is on the horizon? And is it going to be any different with free space or with Earth to ground, or with space to ground?
Well, yeah, there's already discussion initiated in the US, especially. But to be honest,
it would be, wouldn't it?
Yeah, because currently there are like 2 major frequency for optical communication discussed. But I think I don't know, like probably 10, 15 years from now, there's going to be more proper detailed discussion going to be held globally. But as of today, there are already lots of discussion about existing radio frequency bands such as KU, K, KA, or QV is coming as well. So to be honest, we are not too worried about regulation for next 5 years or 10 years.
But if I'm investing in one of your companies, I'm going to be worried about 5 and 10 years' time because that's my exit strategy. So, I mean, to what extent do you think this is going to be something which is happening in the medium term, which I need to worry about if I'm investing in your company today?
Well, good question. Well, in Japan, yeah, since we are operating in Japan, there are only 2 companies doing optical communication in space, and one is us. Basically, government is trying not to intervene in our business. So that's actually one of the things I can tell you now to you and the audience, that our business is not really is kind of stopped or intervened by the government as of today. And we talk with, like Minister of Internal Affairs and also FCC there. To be honest, physically, optical communication has less interference compared with RF because it's, the beam width is much narrower, and potential issues could be caused is, like whether it's eye safe or not, but it's actually not really that dangerous compared with like industrial laser. So to be honest, interference itself is not a big issue compared with RF today. So that's not partly to answer your question, I guess.
Right, is that because just the beam width is much smaller?
Right, yeah.
Right, yeah. So we're halfway through the session now, and I'm just wondering whether there are any audience questions right now that we should deal with. I'll come back to you in a minute. Yes, gentleman in the front row there. I think maybe, are you going to either stand up and yell, or is there an extra microphone? To me you are, but I'm not sure anybody else.
So one part is about the system level challenges, whatever you discussed about. Now another thing is when we are talking about 10 Gbps kind of a data, or 10 Gbps kind of a link, and talking about terabits of links. In that case, how you are coping up with the electronics and the interfaces, because those are also a challenge, because electronics generally don't process in that speed, whether it is ASIC or FPGA. So how you are handling that? That portion, how you are thinking, okay, it will grow in future, or how those further standards, either LVDS or Rocket IOs, so how you will be interfacing optical component with the electronics component, because generation is going to happen at the electronics components.
Pranav, do you want to deal with that, or Nitish? Okay, Nitish, right.
So on the electronics, actually the technology has evolved much more. So while developing, we have to be, don't reinvent the wheel. So there is already high-speed transceivers built into SoC systems on chips that are coming in. So they can raise up to 10 gigabits and all. So what you need to focus on is how do you get your optical signal down to the electrical signal that the transceivers can process. So that's inherently what we are also doing. So even 10 gigabits per length and all that is not a problem. You see in terrestrial fiber optic communications as well. There is 40 gigabits link, 100 gigabits link and all. And then obviously you can multiplex multiple of these transceivers to get to a higher data rate and process. When you're processing the data at the electronics level, FPGA level, you deal with lower clock frequencies, but at the same time you're processing much more data. So your data pipe is much bigger. So even let's say you're running at 500 megahertz, but you are having like 64 bits coming at a time and processing that. So I don't feel that's a challenge. But there's an inherent challenge of how do you, increase the optical signals much beyond that. And there are various schemes being implemented. So one simple scheme, as I can tell, is like an on-off, like you're turning on laser on and off at multiple this thing. But there's also coherent schemes typical of what radio frequency spectrums also use. So you have the sine wave and then you modulate higher signals on that. So that's a fair amount of research also going on there, and it's already implemented. It's already tested. It's actually operational in orbit as well, some of those things. So yeah, so I see 10 gigabits. There is no limitations in terms of any of these things can be readily achievable. The only thing that needs to be taken care when you use satellite comm is, how much is the form factor, what's the point accuracies and all that you like. Going beyond 100 gigabits and all, then yeah, you need to slightly do some novel approach. Terabits per second, I think it's slightly farther. I mean, in academia, it's being tried, it's tested. There are some initial very promising results, but it's going to take time when you want to scale it really to the technology at satellite level.
I have another question regarding the synchronization, because as the speed is increasing, whether there's a criticality about synchronizing the transmitter and receiver in laser comm, or any kind of a synchronization is needed?
So if I understand correctly, you're talking about synchronization between transmitters and receivers, right? So let's say one is the ground station, another is the satellite terminal. So first is you need to acquire the link with the pointing terminals and all. After that, there are standard methods to implement it. You need to do the frequency, first the CDR locking and all that. Apart from that, you need to, once your signal is ready, you will have some synchronization marker on it to recover the data. So again, it is a very standard practice. It's a similar carried forward from what the radio frequency spectrums has been using. So,
is there a fundamental difference between synchronization with an RF terminal and an optical terminal? I was just wondering where the question comes from. Is it just is it just because we're talking about a shed load of greater data rates here? Where does the problem come from?
So that's what actually, when you are increasing the data rate, at that time the synchronization system also need to be worked around that. So is there any challenges when you are going for such a, because RF link doesn't work in this range. So the existing system for the RF link, whatever the synchronization methods are being used, they may not be adequate for the laser link. This is, I don't know exactly. So that's what I'm just trying to clarify.
Yeah,
what are the challenges there? Is there? Or if are, then what are those?
I'll hand it to Pranav, but of course RF and optical are really the same. But why is there a difference, when you move from RF type of frequencies to optical frequencies? Is that just a physical manifestation problem, or is there a fundamental problem in the way you go from classical RF to optical? Is it just a question of your frequency is much higher?
Not even your bandwidth or data rates are also higher.
Right.
So that means you are now, if you are suppose clicking right now at 1 nanosecond, changing the data, now it will be like every 0.1 nanosecond you are triggering the data. So within that window you have to synchronize your system.
Right. So the basic difference is
the jitters involved at lower speed will not affect you much, but when you are going for a higher data rate kind of a system, there that jitter what was sufficing or that was sufficient for the lower data rate, it may not be sufficient.
Right.
So that will be so how that is being handled, is there any issue or it is okay?
So to try and de-technicalize it, if I can, my car does 100 kilometers an hour. My car is now doing 10 million kilometers an hour, and there's a fundamental change in the way in which I have to drive it. Okay, Pranav, I think you were.
Sir, just I wanted to add the Nishit point. Synchronization will be required at transmit and receive end. It depends at what data rate and what modulation schemes you are dealing with. If you are, it is that's why this overall this modulation scheme shifted to this on-off keying based modulation, where this synchronization at that much higher speeds. If you are working at tens of Gbps per channel, single channel, then definitely this synchronization in terms of pulses and the jitter between the individual pulses will be crucial. But that is more critical when you are dealing with synchronization sensitive modulation schemes like PPM modulations. So earlier developments were done using these techniques, but up beyond 1 Gbps, they have switched to this OOK or intensity modulation based technique, where this synchronization is not that critical in terms of severity.
But even if when you are data segregating, suppose user data is there, fine. So you are combining the different users' data, so you have to segregate. So it should not happen the user 1 data and user 2 data. If you are not having a clear demarcation, or if your synchronization system is not up to the mark, in that case you will not be able to pull out the chunk of bits which was for the user 1 and user 2. So there also.
Yeah. This demonstration of around terabits per second link that was demonstrated for a terrestrial based link around 14-15 kilometers, that was 40 Gbps per channel. So the digital portions or digital electronics is matured enough to take care of that much data rate in terms of synchronization and transmit and receive synchronization. Up to 40 Gbps it is already reported per channel.
So let me move on to sort of some non-technical things. Perhaps we can come back to them later on. We've had, there are a fair number of companies out there trying to develop terminals, trying to get financing. why is it taking so long for these companies to raise their finance? I mean, for example, there was one that was Minaric was trying to get financing. They're now saying, well, they're going to break even next year, and it's going to be next year and next year, perhaps. What are the challenges for the investment community? Is it lack of understanding about what the technical issues are? Any of the other things? Hiro-san?
Right. Well, I personally think it's taking time, but it's not too slow. I mean, because it's already existing RF capability is already implemented on the industry, and just since SDA started working on optical communication in 2018-19, those companies, major companies, including Minaric, they started to make hundreds of terminals. That started like 2 years ago. So that's the timeline, and they're already delivering like hundreds of terminals now. So soon we will see more data, and we see more satellites using optical communication. So I think this year, next year, really kick off the market. That's where I think we expect more revenue and stuff.
Nitish?
Yeah. So just to give a gist of it. When we talk about satellite laser comm specifically, it's a very niche technology. It's relying on the upstream value propositions. They're like, who is going to implement it? So there are already geostationary satellites. Once they typically use RF, and that's going to take some time because the satellites they also develop is like 5 years from, and that's not a lot of numbers that you can do. The other market in terms of ISLs are coming up from the likes of SpaceX, OneWeb, and Kuiper. In fact, all of you that you see, they all want to implement laser communications at least at the ISL level, primarily because it saves a lot of cost, spectrum, and there are certain areas where you don't need to put gateway ground stations if you just do ISL. So it's very much there, but because these giants are there, then there's also a challenge how much of it's going to the downstream terminal players as well. So while the volumes are there, it's going to take some time. SpaceX, as you see, I think there are certain, for some of the satellites that are in the polar orbit, they have already implemented it because they don't want to put gateway ground stations in polar regions. It's very expensive. So they started with that. So the technology has been maturing. On the government and the defense or the commercial Satcom, traditionally geostationary Satcom, that's not a lot of number. They're stuck with the traditional manufacturer players and all providing it. So it's going to take time. To put an analogy to it, if you're buying a car, it's someone who's giving you an electrical fully at that, then it's come, or someone who gives you an engine for converting that. That's going to take some time. So that's what's happening in the in this space. So the terminals provider needs to offer it to the satellite upstream, and that can really scale once it matures and more adoption comes in.
But it seems almost too good to be true. I mean, this is like the best thing since sliced bread. Why isn't it getting more financial interest, do you think? I mean, what are the investment community saying? I mean, it seems like it's a great solution. You've got shed loads of data. You've got hyperspectral. We've got terabits of data needing to get from A to B, and there's a really easy solution of losing an optical link. Why isn't it people saying, "Gosh, here's my checkbook"? What are the questions that you're getting about from the investment community who are saying, "Well, I'm not so sure"? Is that a fair assumption about what they're saying?
Right. I think that's the biggest, bottleneck for investor to, invest in this optical sector is probably this atmospheric disturbance. Yeah.
But that's not a problem with free space.
Well, but in order to there is still the biggest the bottleneck for most of the Earth observation or Satcom people is that space to ground in the end. Otherwise, most of the users are on the ground, right? And that bit, I think, currently there are several people trying to say, develop technologies equivalent to say adaptive optics and stuff, but that's not really developed at the level of optical ISL. So that's why it's kind of one with like factors kind of slowing down the investment.
But I mean, is it as simple as saying, okay, I've got one node here which is doing my space to ground, and everything is going through that one node? Or is there a problem with the terabits of information that you were thinking about, where at some point synchronization or jitter causes a problem, where even you can't just feed it all through one node and then have one space to ground link? Well, let me get.
Basically, what is happening, because these terminals,
Sorry, could you tell us who you are, by the way? Just
Yeah, myself Pankaj Gupta. I
and
work
from
with
which company? Yes,
yeah,
right.
I work with the Space Application Center, ISRO, Ahmedabad.
So you work with Pranav?
Yeah,
Okay,
this
right.
colleague. So the basic problem there, what I see is basically lasercom terminals cannot replace the RF link altogether. So there just some caution in the investor, whatever you asked, because you have to have both the technology together. This can provide you the higher data rate, so this can work on opportunistic basis. But for minimal service, you have to have the RF link, so that if you are having a time-bound service kind of a thing, optical link may not be a suitable solution. Now another question comes, what is the current market size and how that market size is going to be? So there I think still there's a not very clear growth path investor may not be seeing, but as RF will not be able to provide the solution for the higher data rate link, they have to go for this optical links in future. Most probably it's a matter of time. This is what I think.
And when you talk about market size, are you talking about market size for terminals or services, or both?
I think I will say services, because ultimately that's what the terminal size is, because few persons start operating providing as a service. They say, okay, don't buy terminal, we will put the terminal on the satellites. You can avail the services, so they can cater to multiple operators. Like there are multiple payloads in a satellite, and they put the terminal on that satellite, and they say, okay, terminal is mine, I can offer the service to different payloads. So this is also a one business model going on in the market.
So certainly Comsys can do the study for you, but let me hand over to Pranav.
Sir, just to add to your question, why US market in this not so much funding is going on, there may be strategic reasons for that, because there are a multitude of application being added to these terminals. So one technology that is developed for one particular application, if you add to this, suppose any DT terminal is there for satellite to ground based link, and you want to do it for ISL, where interplane and intraplane ISLs are needed. So you have to do lot of modifications within that terminal, and that is going to be cost, adding cost to the terminal also. So depending on that, because it is still in the growing phase, and what sir has said, that market, as per a recent survey, this free space optical communication market is poised to grow at the rate of 27% per year till 2031. It is proposed. So it is going to be in terms of services also. So these terminals, since they work at a very high data rate, so for end use services, RF link cannot be avoided. So it is already, there is a mitigation technique. So wherever this satellite to ground based links are there, so internationally, whichever terminals have flown so far, they have put one RF terminal also there to cater to this when atmosphere is not that much friendly. So at least for service should not break. It should continue at some lower data rates. But that is not going to be the case down the line 5 years, because the adaptive optics techniques, and there are many ground station diversity techniques, they are going to cover, provide you full coverage at the most 99.99 coverage throughout the service life of the payload.
Just two nines, 99.99?
99.99%, yeah.
Well, that's not very high for a free space link, surely. I mean, why are you losing so much? I mean, we talk about 4 nines on a satellite link. on an RF link as being pretty good, but you seem to be like only 99.99. I mean, if you're talking about terabits of information, that's a lot of lost data.
But that can be catered with ground station diversity techniques, where you have to establish multiple ground station to provide you full coverage. But a single ground station with you can provide 99.99 coverage.
Let me just see if any other audience questions before we just move on to another issue. No. Yes, the gentleman over there on the left. If you could tell us who you are, who you're with.
Thank you. My name is Gurvinder, and I'm the CEO of QSTC, and we are the Quantum Scientific Technology. So I've been hearing all your debate, and let me summarize a little bit of some of the key issues, because we have been involved in all the quantums as well as the optical communication system. And we are the one of the first or second company which is developing hybrid laser communication satellite. When we say hybrid, that means one way is optical and second way is RF. We are doing both way. So the question what you had was the investment. I'm telling you from practical perspective. When we go to the investor, the biggest question they have is not yet proven. The technology has not yet been 100% proven on the ground. There's a lot of theoretical work done, a lot of agencies work done by ESA, by NASA, but nothing in terms of the commercial output or return of investment has been proven by anybody. As you said rightly yourself, even Monarch is saying in 2 years I will have break even. And any investor, like I have been in front of many time investors, and that's the first question they ask. Now the second question which I don't hear from anybody talking about is I think Hiro-san just tried to mention that about the atmospheric impact. And that's very key important in the laser optical communication. And I have not seen, I have been working with Leicester University, Berlin universities, and many universities in Carleton University, in Ottawa University in Canada. Nobody has been able to tell me that they have an atmospheric model where they can predict the optical or laser communication viability and its successful rate. This is all theoretical. Nobody has a perfect working model as yet. We have been working on a project with NASA for LTV vehicle, Lunar Terrain Vehicle, which was announced last year with Teledyne and Sierra Space. And we are responsible for doing communication from Moon to Earth by two ways, either RF or optical. And that's direct communication or via gateway, the lunar gateway. Till date, we have not been able to successfully demonstrate by a theoretical or by atmospheric model. Yes, it will work, the optical communication from Moon to Earth, due to the atmospheric conditions. There's practical issues are here, which I have not seen here people talking so far.
Yeah, I mean, in terms of the propagation model, I mean, we were working in the 80s with the Olympus ESA satellite about Ka-band propagation, and that time, people didn't really know what was going on in terms of the propagation measurements. I mean, that's going to be exactly the same question with optical, is that right?
Exactly. I remember 1999 having a discussion on Ka-band. Hey, it will never work due to the weather condition and propagation will not work. And we improved. But we haven't learned the lesson. We are not doing that. But we have been working for over 2 years to develop that propagation model for atmospheric model where we can predict the behavior of an optical communication or laser going through free space optics going through the atmosphere. Because believe me, it's not the same condition as optical and RF. Although you can say that, the end results are the same, but they are not same. We are talking about 1332 nanometer, very millimeter wave. And so that's what RF talking about. So there's two different things you're talking about.
Let me hand over to Hiro-san because he's gagging for it.
Yeah, because, yeah.
Okay. Let's get an answer from Hiro-san and then we'll come to you.
Okay. I try to be quick, so yeah. So, second gambit, the point you mentioned is actually the second bit, especially. There are several people trying to do the same for propagation model these days, especially in Europe and US, basically measuring using IoTs. And the way I say, adaptive optics equivalent technology is the one to basically offset the atmospheric disturbance. But adaptive optics, some people here probably know that it's technology developed for astronomy. It has like decades of heritage, so it works, but it's expensive. I was like, working in Cambridge doing astronomy, so I personally use it as well. You need like postdoc or PhD student operated to basically utilize this deformable mirrors. But it's very expensive, it's not for commercial. People are trying to make some FPGA-based very cheap technology. That's really coming soon. So that probably is a driver to, solve the issues for the second point of your question.
Yeah, I was going to add to that we are working on FPGA-based BEMS, what we call bit error correction method. And that's what's trying to going through the atmospheric implications and impacts. So we can improve a little bit more further efficiency and usability of the free space optics. But it's still not 100%. We still have a lot to learn before we can say, yes, we are there.
So who's paying for all this research? I mean, basically, the finance, let's just say I'm doing due diligence as we do on behalf of a financial guy. The guys are going to say, yeah, well, you want the money, you pay for the development and the research.
Right now, in Canada at least, we have a one quantum program, and we have at least 2 satellites going up very soon, which will be showing an optical communication system by 2028. And we even have a quantum and optical communications society in right now with Canadian Space Agency, McMaster University, Carleton University, NCRSC. These are the organizations which are funded by the government.
So basically, going back to the question, yes. You want the government to fund it. You're not.
It's already been funded. It's already been funded. It's already been. We have about allocated $120 million for the next 3 years.
But not your money. You want the government to pay
partially
for it.
You have to do. It's not 100%. You have to develop something on your own. Like if the government gives you 75, like a typical R&D credits, you get 75 and then 25 you have to put off from your own pocket.
Right.
You still have to put something. You can't expect everything but to be done from the government. And now one thing more, you had asked another question about the regulatory.
We've got a couple of minutes. I just want to say if there's any other questions we can deal with before we, otherwise we'll, in that case, we'll go back to you. Okay.
So Jeremy, you had another question about the regulatory. So I think if you remember, Hirosan, last year we had a discussion and there was a document issued by NASA, a draft version of the document to control and regulate all the optical communication and free space optics stuff. And there is already in process of how to regulate all this of free space optics and everything. Correct, including space terminals. I think you forgot about that. So we discussed it last year in April during a small Satcom symposium. Mm-hmm. So it's already we already have a roadmap. In ESA also issued the same sort of standards.
So let me just ask in the last minute or so, Nitish,
So see, in terms of regulatory, let's not mix it with the regulation that RF spectrum has. So RF spectrum first has a spectrum licensing. Yeah. So see, RF spectrum, when you do it, you have RF spectrum licensing that you have to do. You have to pay for the spectrum. For
I'm sorry.
Yeah.
I know very well.
Right.
Yeah. I'm not talking about RF spectrum. I'm talking about specifically optical, free space optics regulatory body, and the specification and the draft technical specification issued by ESA and NASA deals with only and only the free space optics or laser communication.
Exactly.
Nothing to do with RF.
Correct. So the SDA ones, basically they are trying to standardize optical system links. So they are releasing technical specifications for, what should be the link range, at what minimum bandwidth it should work, what should be the speed like, what range is pointing at. So those sort of standards are coming up. But I will necessarily not put it in the bracket of regulation. It's not regulation.
It's all very interesting, but we're into tea break, and I want to just wrap up if I can in the next minute or so. Pranav, I'm not that desperate for a cup of tea, but
yeah, regarding regulations, this is SDA standards are there for their transport layer terminal development. So it is meant for the interoperability of terminal to fund many partners who can contribute for their transport layer optical communication development. So they are just putting their requirement in a way that many partners can play interoperatively. But it is not going to the case with all over the world. Many countries are working because it is for ISL type of terminal only. But with the same terminal, if you want to communicate with cross-plane links or to ground, so the pointing tracking mechanisms going to be different than what they are regulating. They are going with the beaconless acquisition, but somewhere you may need a beacon for acquisition process also. So in a way, it is not regulation. They are coordinating their requirement with their industry partners so that they can work interoperatively. It is to be interpreted like this only.
So, as usual, we've got technical problems, we've got regulatory problems. I'm sure there's plenty more to discuss, hopefully at the next Congress. So Nitish, Hiro-san, and Pranav, and the audience, thank you very much indeed for your questions, for your insights, and look forward to seeing you next time. And SIA, thank you again for organising a great event. Thank you all.
Very much indeed, sir. Ladies and gentlemen, let's put our hands together for that wonderful session we had. We can have a round of applause again. Thank you. Thanking our distinguished chair and moderator and all our eminent speakers, we now close this session. We will have a short tea break. We are left with about 25 minutes for that. The next session commences at 12 o'clock. And the topic which will be conducted here will be satellite IoT playing to its potential. But before we close, ladies and gentlemen, we have another important announcement to make, that from 3:50 p.m. onwards, we will have a session on startup and investors meetup here in this track 3, which is being powered by Invest India and SIA-INDIA. All the startups are kindly requested to assemble here by 3:50 p.m. for that session. Thank you very much indeed. Please enjoy your tea and coffee break and be back in time for the next session, which will begin at 12 o'clock sharp. Thank you.